Could you give a short introduction of yourself as a lecturer and the subject being taught, which is electronic circuit design?
So my name is Ranjith. I am an associate professor at Electrical and Electronic Engineering Department. Well, I come from an aerospace background. I was involved in some interplanetary missions in the past, developing sensors, sensor electronics, and then moved on to integrating nanotechnology onto electronics platform. So my research area is broadly, well, you can say sensors. So I work on different types of sensors, spanning from electronics to photonics, designing new type of imaging sensors, chip designs. The subject is, I would say, a fundamental subject in electronics, teaching the concepts of electronic circuits. Because most of you, especially those who came from the Melbourne model, they have already learned up to the diodes and how you can make transistors using 2p-n junctions. So we will be starting from there. But then having said that, the strategy that we are approaching is once you are into circuits, two ways you can learn circuits. One is to randomly learn some circuit concepts like what is a current mirror, some differential amplifier, something like that, which is okay, some students. Then later, you pull together things and make sense of it. But the strategy what we are adopting is a top-down approach. The former one, I would say, is a bottom-up approach. You learn a lot of random things and then put together. But what we are doing is based on our experience. Bottom-up approach is good, but then it might not help all the students. A top-down approach will help. So how we are teaching the circuit is we will start from the place where you stopped in the electronic device modeling. For the students who are coming from the Melbourne model, and there will be students from overseas, lateral entry students. And so for them, maybe beginning of the transistor, how transistor works, how it can amplify current. Towards the end, you will be learning current mirrors, differential amplifiers, so on, so amplifiers, the basic circuit concepts, and then you also will be understanding how to design an operation amplifier, because that will help you in designing complex circuits. Not only that one, there is something that is going in parallel. Though I said it is a fundamental subject, yes, it is a fundamental subject maybe to start with, but it will increase the complexity. And you will be learning small signal model analysis, because small signal model analysis is the backbone of chip design. So if you don't know small signal analysis of the circuits, you won't be able to design a chip. And in the lab, we will be using analog discovery, so that you will be breadboarding the circuits starting from simple amplifier circuits, and the complexity will be increasing towards an operational transconductance amplifier at the end.
So what exactly can students expect for the workshops in this subject?
In the lab assessment, we have got two components, well, three components. One is a quiz. We ask some questions randomly before each session to students to make sure that they understood what they are going to do. Then that carries some marks. And then there is a check-off, means you will be breadboarding, and then there is a check-off point. Then you will be getting a particular signal that you have to show to the demonstrator. Then you will be submitting a report as well. So then, yeah, basically, the good thing with electronic circuit design is either you can do your breadboarding during the lab time, or you can do it outside. But whichever way it is, you may have to show the check-off points, the circuit working in real time to your demonstrator or your tutor.
Just coming back to the background of the subject as well, could I ask what excites you the most about this subject specifically?
Oh yeah, because as you know, I come from a high-speed electronics background. The most exciting thing for me is maybe small signal, because many people learned transistors, maybe amplifier circuits, how to design complex circuits. But the small signal is another component maybe people haven't looked at, because that will give you another insight, because not the DC resistance. So we are talking about impedance, input impedance, output impedance, small signal gain. So these are all these parameters we might not be able to understand without the help of small signal. I've got a couple of coffee questions, so I will announce those questions, and whoever is answering those questions, I will buy them coffee, and then I will also show my lab. This electronic circuit design introduced analog discovery for the first time in the university back in 2015, and the analog discovery, the good thing is you will be learning how to design small amplifier circuit, and then we are increasing the complexity so that you are breadboarding, and you are making an operational transconductance amplifier. Plus you have got some options. Options means those are the extra miles. If you want to go, you can go, but you get some bonus mark. Theory and practical both are going in shoulder to shoulder, I would say. So maybe that is the why I am excited. Like small signal model, that is very theoretical circuit analysis. At the same time, you got a lot of hardware. Both are going in parallel or in line or in shoulder to shoulder, something like that.
The next question I had is, how does it contribute to the electronics and photonics specialization?
This one is teaching the basic concepts of circuits and how you are building circuits, chip design aspect. Then that also will help. Yeah, this is one of the main subjects you should be taking, even if you are not specializing in electronics and photonics.
What are some like exciting innovations or prospects in this field that the subject relates to?
Because we are teaching a small signal model, we also will be touching upon the semiconductor process technology. When you are reducing the size of the transistor, as I mentioned, when we say 7 nanometer technology, that is not the size of the transistor. Actually, this is the length between drain and source. Then we will be teaching you, what are the challenges when you reduce the size of the transistor. Now we are coming closer to the quantum mechanical regime, how that is improving the speed and the power consumptions and the noise. When things are closer, is more prone to noise, and then how IBM mitigated the noise in the fin design, recent one.
Another question I had was, what can students learn from this subject that they can potentially bring to other fields in engineering?
You will be able to use the concepts in breadboarding a circuit, maybe for the capstone, or later you might be working for an industry, or wherever you need to quickly build a circuit where you don't want to design a PCB, but you can breadboard. Even if you are doing other areas like control, and suppose you are making a PID controller, then you might be able to breadboard. Definitely this skill you can take it to industry, you can take it to your own hobbies. If you want to build some circuit later, or you are going to biomedical area, maybe everybody should know some fundamentals of the circuits.
What type of student do you think this subject is most suited for? Like those that like working hands-on, or more theory related, or a bit of both?
Yeah, I think it's both. Yeah, both the students will enjoy this one, because there is a bridging between both theory and hardware. I'm pretty sure both students who are interested in more theory and hands-on will enjoy. Another advice I will give to students is, don't get panic, because we have written an extensive lab manual and all the circuits, small signal. Sometimes students might get a bit scared at the beginning. Oh my goodness, I can't imagine I need to learn this much. But once you learn, started learning, you will be fine.
Is there anything else that you would want future students to know about the subject before they start?
Maybe it is a good idea to brush up your knowledge on diode circuits, because our assumption is these things. I would recommend if you are around, please come to the campus and make use of the facilities as well.
Definitely, yeah. After that much online uni, and I agree. Like, I feel like the best learning happens when you're under a bit of time pressure to figure out what's wrong, right? Whether it's a broken circuit or it's a mechanical thing. Yeah.
When I was a student back in the UK, I also attended the subjects, something similar, and some practical things, sometimes can be difficult, but better to be patient and trying to figure out. And also, it's a good time for students to develop some self-learning skills, because when I went to industry, they asked me to do something I never learned. when I was in the space, especially in the space industry, then I couldn't say, okay, hang on, I will go to the uni, learn that thing and come back. You know what I meant? So you need some self-learning. I wouldn't say that you self-learn the entire thing, but you know this much, then this is kind of related, so that you should be able to learn, because you know this much. So that also is a good time for the students to learn, because you are coming to the masters. When I was a student, I asked my teachers and then I learned. But now, as a lecturer, I learn from your questions. So I would, encourage you to ask some good questions.
That's so true, though. Like, just especially, I feel like at a master's level subjects, with how complex things are, people can have like radically different perspectives and approaches to a question, and they can both be right as well. And it's always interesting to see the way other people approach it.